Welcome to Programming in Modern C++. We are going to start week 10 with module 46. In the last week, we have spent the time on standard library. We have familiarized with I/O libraries both in C as well as C++. We discussed C because those can also be used in C++. We learnt about generic programming, which is a very great style to adopt in terms of C++, and then we have familiarized with C++ standard library with specific focus to standard template library or STL, and familiarized with containers, iterators and algorithms. Going forward from this week, from this module, and for the remaining part of the course, that is the 3 weeks, we will primarily focus on the modern part of C++. So far we have been discussing about C++ 03 primarily. Now we will start getting familiar with C++ 11 and beyond. These discussions will be primarily on C++, but we will keep on mentioning additional features that came in the subsequent versions in 14, 17 and 20. In this module, we will introduce the few general features of C++, auto, decl type and suffix return type. So, this is the outline which will be available on the left panel as usual. So, first let us look at the major C++ features. And just to remind you, these are the different standards that we have been talking about. C++ 98 or its corrected version C++ 03 has been in our discussion for all the time. C++ 11 is what we are going to discuss now with references to 14, 17 and 20, the latest version. In C++ 11, several core language features have been added onto C++ 03. Some of them were like to make it a better C++, like when we started studying C++ 03, we noticed that there are quite a few features which just made C++ a better language over C. Similarly, C++ 11 also has a number of features which make it a better C++, but there are number of features which are fundamentally very different, fundamentally I should say very significant, and some of those I have shown in terms of the bold Rvalue reference, move constructor and move assignment operator semantics, the lambda expressions, multi-threaded memory model, concurrency support and so on. And there are several others which are either convenience features that make C++ more amenable to generic programming and easier to write correct code, or they are features that are required for these advanced semantics to be provided in C++ 11. We will go over not necessarily each one of the features, but we will take up most the major features while we discuss. Besides the core language, there have been significant additions to the C++ standard library. So, if we look at the standard library, on the left column, there is a list of headers which have been added to C++ 11 standard library, and naturally they have lot of different concepts added. So, some of the important features are of the library as added to C++ have been given on the right column. We will discuss some of them as we discuss the different features. Now, to start with C++ general features, we start with auto and decl type for type deduction. Auto, as you know, was a keyword in C++ 03. It used to mean automatic storage type. This is one of the very few rare features which have been deprecated from C++ 03 to C++ 11. So, that meaning of automatic storage type is no more applicable in C++11. In C++03, while we are specifying an object, it is necessary to declare its type, right, that we know. It is a strongly typed language, so we must declare the type, and we may include an initialization with the type as well. In C++11, there is some liberation being given from that requirement if a variable has an initializing expression, which usually most variables will have, recommendedly all variables must have, then it is possible to just write auto in the place of the type specifier, and the type will be deduced by the compiler from the initial type of the initializing expression. So, we see the simplest example here. I am just writing auto at this point, and my initializing expression is a integer literal, int literal. Therefore, I am not writing explicitly. So, this is equivalent to writing int x initialize 10, but I am not writing this int. Instead, I am just writing auto, and the compiler will be able to deduce that. So, this deduction is very similar to template parameter deduction that we had talked about earlier, and we will soon see. Here actually it does not show a great advantage, but soon we can see that it has several advantages. For example, consider this map. We have just studied map in terms of the containers. So, it is a map whose key value type is int and value type is string, the map M. So, as a map it will always have an iterator, right. So, you know that map container type has an iterator type. We have discussed this while discussing map. Now, this is a long expression, and it is quite possible that while writing this you will forget some details and the compilation will fail. So, what you can do, you can simply write auto for this. So, what it will do, you are writing m.begin, m.begin returns an iterator. So, the type of m.begin is the iterator of the map type that you have given here, and the compiler will deduce the entire type expression on the right from this auto. So, that is a big convenience to really have. You can also have constant and volatile or reference or pointer adornments that you may add. So, you can say const auto star ampersand x, where x1 has a auto type to 10. So, x1 is int. So, when you do this, you are basically taking the address of an int. So, you have int star, and then you are adorning with const. So, you have a const int star as the type of x2. Similarly, you can do a const reference in this way to the entire map, which becomes a convenience, right. So, you can have const iterator types done as auto in the similar way, except that you will have to remember in place of begin, you have to use the iterator member function for constant iterator, which is C begin or C end, any one of those you can use, or C reverse begin or C reverse end, all of them have const iterator type. So, you can use it simply in terms of the way the template type deduction is done. So, given a template function f with type parameter t, f expression will deduce the type of t from the type of expression, right. This is the template type deduction, and exactly the similar thing will be done by auto. So, auto in most of the cases is very simply template type deduction given to any normal part of the declaration code. So, variables for variables that are not explicitly declared to be a reference, the top level const and volatile in the initialization are ignored, and array and function names, when they are being initialized, used in initialization, will decay to corresponding pointer type, right. So, this is auto will take the basic type that it has. So, I have a const list of int, but when I do auto v1 of that, I actually get just the list of int, I do not get the const part of it. So, that is stripped off. Similarly, if I do a reference, which is, that is why it said it is not explicitly declared to be reference, but when it is explicitly declared to be reference, it will take the entire type and then add the reference to it. So, this is the basic connotation of or the way Otto puts the type. Another example, there is a array of size, buff size of elements type float. If you just do auto, it will decay to pointer. So, element type is it is an array of float. So, it will become float star, as you know. But if you use a reference, then it will preserve the entire type and give a reference to that. So, the type is float array buff size, and you are doing a reference. So, you get a reference here. So, this is the type that will get deduced. Using auto, you can use both direct initialization as well as copy initialization, as you know, and in auto both these syntaxes would have the same meaning. We will see in some other context slowly things will become different. Now, auto is related to another feature called decl type, which has extensive use in templates. Just to start introducing the problem, suppose I have a multiply function which takes elements of two different types t and u. I do not know what these t and u are, and multiply takes for these two types, it takes two references of constant vectors of t type and constant vectors of u type, right. So, basically possibly I am trying to do a inner product of two vectors and so on, whatever. Now, the question is what is the type of the product of the elements of V t and V u. So, an element of V t is V t I, an element of V u is V u I, and I am multiplying them as I am doing here. The question is what is the type of this product, right. That depends on the type t and u, and the question is how do you express that. And this is I mean this use of auto here can be a big convenience, because otherwise you will have to spend a lot of effort to really write a type expression which will work for any type t and any type u. So, let us see what you can do. You can use decl type in this context. Decl type yields the type of an expression, sorry, decl type yields the type of an expression without actually evaluating it, right. So, it just like something similar you will remember is available for size of, right. Size of also does not, takes a type or an expression. If you give it an expression, it does not evaluate the expression, but gets the size of the type of value that the expression actually represents. So, let us say in decl type what you can get. So, I have a declaration for an int x and a pointer to int ptr. Now, if I put decl type x, it will take the Eli's type and make it int, right. If I take decl type ptr, it will make the type of p1 as int star. Similarly, if I take say something like decl type ptr44. Now, what is ptr44? ptr is a pointer. So, when I write ptr44, I am thinking of it as an array of elements. So, this is one element in that. So, it has to be of the integer type. Now, this ptr44 I have neither allocated nor done anything. So, I cannot do an evaluation of this, but without evaluating, the decl type will find out the type for this. So, it sees, I mean it looks like it is something similar to auto, but we will soon see what the advantages are. There are certain specific differences in terms of how you parenthesize, but these are rare exceptions and you can always look up the manual for that. Now, we get back to the example of that multiplication kind that we were doing. So, I want to find out the type of ai times bi, where a is a constant reference to a vector of type int, b is a vector of type float, and so what will be their product type, right. You can, looking at this, you can easily say that it is int times the type denoted by int times float. So, whatever questions and all that will happen, but how do you write that? You will be able to write that by Deckel type A0 into Deckel type B0. Now, here I have taken the example of int and float just to make it easy for you to understand, but this could have been a type T and this could have been a type U. Even then, the type A0 will be of type T and type B0 will be of type U. So, their product has an expression and you can do a Deckel type on that to find out the type. Mind you, we are not again doing any evaluation. So, the difference with auto is, auto we will need to have a specific variable for which it is finding the type, but here you are just taking the expression and finding a type without associating it with any other variable, and that comes pretty handy in terms of doing the expression. So, let us see how does auto and Deckel type kind of are similar as well as they are somewhat semantically different. So, first consider a set of declarations there, int a, int reference, const int reference. So, if you check the type of all these variables a, b, c, d, you will get the corresponding types as written. Now, if you do an auto using these respective variables, whether the variable is of type int or of int reference or constant reference, auto will always, what it will do? It will strip off. It will strip off the const, it will strip off the reference, it will just give you the basic type. So, all of these will be int. So, if you have to put the CV qualifier or reference, you have to add that explicitly. So, if you do that using a, which is of type int, and you say auto ampersand, this will become int ampersand. Similarly, if you do take a and use const auto, then it will become const int. So, you have to explicitly put that. In contrast, if you use this if you do this with Deckel type, then you can simply write Deckel type a. What does Deckel type take? It takes an expression. So, a is an expression, it is a variable, so it is an expression. So, it will give you the type of a, which is int. This part is same. But if you do Deckel type b, you will get int ampersand, which was the actual type of b. Auto was giving you just the int. So, Deckel type differs from the auto is that it does not do this strip off of reference pointer or const, volatile, etc. It gives you the actual type that you have. Right. Now, in C++ 14, you have another version of Deckel type, which just uses the word auto in place of the expression. So, what this means is this auto relates to the initializing expression. So, when you Deckel type auto, a dt auto, it initialized with a, it will take the type from a. Similarly, here it will take the type from b, and correspondingly it follows the Deckel type semantics, and it will give you the corresponding types. So, this part is just that you need to learn and remember. Now, the question certainly you might come to is, well, if you have, as a programmer, how do you know using auto or Deckel type what type actually the compiler is inferring? This is happening at the compile time. So, at the runtime you have no way of executing and knowing that. So, C++ also does C++ 03 also does lot of inferences in terms of implicit conversion, templates, and so on. C++ 11 in addition is inferring for auto and Deckel type. The question is, how do you get to know that? Unfortunately, the compiler does do the inference, but there is no support to let that infer type known to you. for the simple reason that the compiler's job is to translate it to a program which you will execute. Compilers is like a service provider. It is not supposed to give its internals to you. So, how do you actually know the type that has been inferred? One way could be you can use your IDE, the debugger particularly, run the program and do a breakpoint, and at the debugger you can see what is the type. Debuggers usually give that information. This is clumsy, as well as the difficulty is you will be able to do this only when your program compiles. Suppose you need to know the type that has been found by auto, that has been inferred by auto or Dickel type, and because your program is not compiling, it is saying that there is some error. So, how do you get to know that? So, there is no standard way, but I have given you here two possible hacks that you can use, and I have given the references of where these have been discussed at greater length. One is you can just declare a template, but not define it. So, it is like a forward declaration. You say knowledge type is a template of with a type parameter t, but you have not said what is that class is. Right? Then suppose you have an array int ARR, how do you get to know its type? Its type is int3. So, what you can do is you try to instantiate the template with the Dickel type of ARR. Right. So, ARR is an expression because it is a variable, it is an array of size 3 of ints. You do try to do a Dickel type of that. This type you are trying to pass as t. As you do that, so you are trying to instantiate that template, but that template has not been defined. So, the compiler will not be able to instantiate the template. So, what will do? The compiler will give an error. So, for example, this is this error message is particularly from this online compiler. You can try this out. So, in the error message you will see that the type inferred is embedded, right, because compiler is trying to tell you that this is something which is wrong. So, it cannot be, it is an incomplete type, it cannot be defined. Other even simpler way to do this is not even trying to do a template, but just do Dickel type ARR : say underscore. Underscore is a name of a variable, right? Any variable name can start with an underscore. Now, what does this mean? This you are doing Dickel type ARR : which means this is a type. So, it is saying type : something. So, it is expected to give you a class or an enumeration type. Type : syntax basically means that, but there is nothing that actual type is int3 and it is not a class, it is not an enumerated type. So, the compiler will not be able to interpret this particular statement that you have written. So, the compiler gives you an error, it says Dickel type evaluates 2, and that is what you wanted, to know what is the type that Dickel type is inferring, which is not a class or of enumeration type, which is a very quick way. I always use it to know what is the type of an expression that is being inferred. You can use it in any context. It is a very nice one line hack which will give you the information through compiler messages. Of course, you can use type ID operator also. We have talked about type ID operator during dynamic dynamic polymorphism, but it is not a good thing to do because it is meant for dynamic type, but you can still apply type ID on anything. So, if you do that on a, so this is your original variables. So, what you need to do is type ID, pass the expression, variable name, and then do dot name. Type ID returns you a structure. So, dot name has the name. So, for x, which is an integer, you get as I, this c. Now, if you try to do this on vector, which are basically having these types, you get these kind of strings, which are compiler's own internal representation of the type that the entire thing means. So, by type ID you can get the type, but it is in a format that is very difficult to decode, right, and it is compiler dependent. Use a different compiler, you will get a different coding. So, type ID method to know type is not actually useful. You have to use one of the two hacks that I have just discussed. Okay. Now, let us using Otto and Deckel, let us look at a very interesting feature that C++11 has introduced called the suffix or trailing return type. The question is, when do we need a Deckel type? When we have a variable, we can do Otto on for that, but when we do not have a variable, then I need to use Deckel type. I cannot do an Otto, right. So, what is that? When do we need a type where there is no variable? When that variable is temporary, for example, in a return type. So, let us say I am trying to define a multiply function of template type parameters being t and u, the expression is x times y. The question is, what do I write here? In terms of t and u, I have to be able to write the return type, but I do not know what to write. So, I know the type to be returned is the type of x times y, type of x times y. So, I say okay, not a problem. I will just use Deckel type on this. Deckel type should tell me the type. So, I will do Deckel type x times y and I will write the function. This will not compile. Why will it not compile? Because the compiler checks the code from left to right. So, it comes across x before the scope of x has actually started. Scope of x starts, type is defined here and the scope starts here, but you need to know x at this point. Similarly, you need to know y at this point, right. You cannot know that. There is no way to know this. So, this because of the scope problem, you cannot use Deckel type directly there. Okay. So, if you are a very smart programmer, you might want to do something smart to get there. What you said, okay, I can always use 0, it is a constant, stands for the null pointer, right, and cast it to Deckel type, cast it to t star. So, I take 0, which is which does not have a type, or it is an integer type, I cast it to t star. So, I get a pointer of t type. Similarly, I get a pointer of u type. I dereference, I will get a object of u type. I dereference t type, I will get an, I dereference the second one, I get an object of u type. So, if I mark it well, then this is an object of t type, this is an object of u type. I am doing the same thing as this, but I am not using the name x and y, and then I multiply. This is a multiplication, this star is a binary multiplication, right. If I do that, certainly I will be able to get what is the type of x times y. But certainly, as you can see, this is a very clumsy and error prone way of doing it, and in general it is difficult to write this kind of expression. So, what suffix return type, a trailing return type does, it pushes the return type to the place where it actually belongs, that is after the function. So, what it does is, in the usual traditional return type position, you just write Otto, that it will be deduced, and then after the function header and before the function body with an arrow, you put the return type. This is available in general, and in that you say that the return type is Deckel type of x into y. Now, the advantage is x is already in the scope, y is already in the scope. So, x and y are defined symbols, you know their types. So, you can deduce, the compiler can deduce the Deckel type. The only thing is you are placing the return type after the header, not before the header. Before the header, you just have a placeholder to say that I want the compiler to deduce this, right. So, this is what is called the suffix or trailing return type mechanism, by which you can let the compiler deduce that. And actually, if you think of it, this syntax, this suffix syntax is not necessarily about templates, it is about scoping. It is type deduction in a scope rule, because scope is what you are not getting. For example, if you have a list of link elements, and if you have a member function erase that takes a link pointer and returns you a link pointer, then outside of the class, if you outline the body of this function, then you will have to write it like this. You will have to write list colon colon link star and then list colon colon erase. Now, this list colon colon link star is required because you get to know that this is a member function of erase, the member function of list only after you have come to this point, but you need to know about link star before that, right. So, you need to write it twice. Now, what you can do, you can just write an auto here, that is you are not writing this, you are just directly writing the member function. So, you write auto because this is necessarily the return type, and then you put the return type as a suffix pointer link star. So, there is no specific qualification for the link that you need, because you will be able to deduce, compiler will be able to deduce that from the suffix notation itself in the auto, right. So, this is how the Deckel type specifically help you in doing variety of different deduction, and you can, as you can see, we can use it in C++11 as we have seen this, we can use it in this form. When you come to C++14, you get something which is even more interesting. You can, the suffix type, this suffix type specification, if you see, the only problem is it has to write the return expression twice, but then the compiler knows the return expression. Why do I have to write it twice? The compiler can generate this entire part itself, right. That's a simple common sense. So, C++11 just allows you to write auto. It is like any other function that you write, just you can write auto. Of course, for backward compatibility with C++11, it will also allow you to use the suffix return type, right. C++11 introduces another which is Deckel type auto, right. So, you can write Deckel type auto also in place of just auto, but if you use Deckel type auto, then you will not be able to write the suffix return type, because it does not need a backward compatibility. Deckel type auto was not there in C++11. So, we will present a simple example to show what is the difference. Here you have, I have defined three functions, foo bar and foo bar. Now, if you see here, then okay, the first let us look at the parameters. Parameters are going to be struct A or struct B, both of which have a member function value. This returns by reference and this returns by value, right. Now, the question is, so in each of this function I take t as a reference of type t and return this. So, basically the body is the same. Okay. Now, how does the semantic differ if I write auto, if I write auto ampersand, if I write Deckel type auto? If I write auto, what will happen? Auto strips off all reference and all that, right. So, if I try to do foo A should return you a reference, and therefore, you will think that since it is a reference, I can make an assignment to it. So, I can say foo A assign 20, but this will be an error, because auto will strip off the ampersand, will strip off the reference. It will just return a type int, which is an R value to which you cannot make an assignment. Whereas, if you do foo B, which is doing not trying to assign, foo B simply has an int type, it applies that and forgets the temporary result, it is fine. Similarly, if you try to do it on bar, where auto has an ampersand, then auto will necessarily put the reference in every case. So, now if I do foo bar A, I will get a reference to int, L value will be type of int ampersand, and it will be fine. But if I try to do foo bar B, then I have a reference, and a reference without an initialization is not allowed. So, I will have an error. In terms of Deckel type auto, it will figure out what is the actual type. So, if you call it with A, it knows that the type is int reference. So, it will allow it int reference. If you call it with B, it will figure out that the type is int, it will give you a type int, and both of these will be correct. So, that is the difference between using auto and using Deckel type auto. So, here are some common recommendations that I have put, you can go through that. And so, this brings us to the end of this module, and we have introduced 3 general C++ features of auto, Deckel type and suffix return type. Thank you very much for your attention. We meet in the next module.